Thank you for joining us today. So, like Sharada just said, this will be a hands-on activity. So, if any of you are interested, you can go to the ISCB website and then go to the agenda tab, program and agenda right here. And then you should see on Wednesday, May 14, you should see a GitHub link. I can give a couple minutes to set up. So once you hit the link on the GitHub, you come to this page and you will see session 3, 4, 5, and 6. This will be for the rest of our evening here for the hands-on session. So right now I'm going to kick off with session 3. If you click into session 3, you'll see this session 3 notebook. You can click into it. And it will come here, and then you just say open in Colab. Click this button. It should bring you to this Google Colab right here. You don't have to download anything. You can just follow along. The first 5 minutes will be my introduction, and the next half will be or hands-on coding. You don't have to write any codes. You just have to hit the play button together and then to see results. And then you can keep the code if you want for reproducibility for the future use if you want to. Okay, so a little bit background for myself. I'm a PhD student here at University of Minnesota. My main background is doing research on chronic subdural hematoma. So you have acute subdural hematoma and you have chronic. Chronic means over time. So you have blood in your head, or slowly the blood leaks overhead inside your head. It happens more commonly in older adults, and then so the blood just slowly sipping through it. You don't even realize it because it's such a slow process. And then when you get a CT scan, you will see chronic blood and not fresh blood, not like an acute after an accident type of blood. It's more commonly found in elderly adults. So the clinical symptoms will be like very, very common headache, confusion, vomiting, aphasia, stuff like that. And then the current challenge is because there's like different type of techniques, and then because this is a slow and gradual things, so when you drain the blood, it leaves like a big hole still in your brain. Your brain have to slowly regrow to fill up the space. So more often than not, you have reoccurrence in the patients. So my research project is mainly focused on how do you calculate the best drilling point angle to drain the blood so that the patients don't have reoccurrence. That's the goal of this whole project. So this project is separated to 3 different aims. Aim 1 is using machine learning to detect chronic subdural hematoma. So as you can see, this is like a slice of the brain scan, and you can see the hematoma is over here. If you outline, it's like a crescent moon shape right here. So look at the darkest spot over here. It looks actually very similar to this color. So we have to train the machine learning to how to separate this blood, but not picking up this intensity as well, because they kind of look the same. For machine learning, they are not like us, determine like, oh, next to a skull, stuff like that. They look at the colors. So I have to train the machine to see, to accurately identify the hematoma, but not other things. So I use a very basic 3D unit, and this is the segmented version of it. So coming back to aim 2, is to after you segment out the blood. So here we are going to predict what is the best drilling location so that the patient won't have to suffer from reoccurrence and come back for another surgery again. So this is the aim that I'm still working on. And the third, last but not least, aim is the most fun aim that we have in this project, is after we determine the drilling point, we want to be able to put it into an AR so that when we calculate the drilling point, we can just put an AR and then have the patient's head and everything inside the AR and then overlay into the patient's face, so we know exactly where to drill. So currently, neurosurgeons just guess. They see the hematoma and then they just follow the landmarks from your facial structure, and then they just think like, oh, I think this is the best drilling point, but they could be like a couple off, like we don't know. So the main goal is to able to use AR to calculate the best, to see that we calculate the drilling point before, so now we have to put the drilling point into the AR so that you can overlay into the patient, and then we don't have to guess where to drill, but we know where the spot is. So that is the whole goal of this project. So what is TBI? The most common cause of TBI, or traumatic brain injury, I should say, is falling. So people like fall from the stage, or when they walk and they trip. This happens mostly in elderly populations again, and then or accidents, vehicle accidents, stuff like that. And obviously, there's many different types of hematoma in the brain. So we have epidural. Epidural means above the dural, and then you have subdural, which is below the dural. And then you have subarachnoid hemorrhage, and then you have the intracerebral, which is inside the brain, or you have intraventricular, which is inside the ventricle in your brain. So how do they look like in CT scan? So IPH is also another word for intracerebral. You can see like this very bright color. That is the acute blood. So remember just now I told you chronic blood versus acute blood. Acute blood, you don't see this type of density, the color in your brain. So machine learning generally picks up acute blood very easily because the intensity of the acute blood is so not similar to the brain versus like just now how I show you the chronic blood, which is like a little bit over here. They kind of like camouflage into the brain. And the IVH, this is ventricle inside the ventricle. This is subarachnoid. And then this is the subdural hematoma, which what I am working with. But this is, again, an acute blood. I'm working with chronic blood, which is way more difficult to train a machine learning on because they are very similar to the brain. Just scroll down a little bit. This is epidural. How to differentiate epidural to subdural is the shape. Epidural has a biconcave shape because it's above the dural, versus subdural, it is like a crescent moon shape because it is underneath the dural. And then the last patient, unfortunately, this person has many different types of hematoma. So, yep. And then, so this for the CT scan is, yes?
Yeah, so basically the white pixel intensity is the same in these like images, but like you look for shapes to differentiate.
Yes. So your question is why do the intensity look the same but not the shape?
No, I mean like I don't really know like how this condition is displayed in images. I'm asking basically, so the condition, whether it's like ABCD or something that's like these white stains, right, that you highlighted. And so like how you want to differentiate them is by like shape.
Yes.
So
Yes.
not by the density of pixels.
No, density of pixel is about how long the blood has been in your brain. So the brighter, the fresher, the darker, because your body tend to, very good question there. So your body tend to, because it's a foreign thing, right? If you have a blood in your head, so your body will work towards it to like reabsorb it back to your body and try to like digest it, like how we eat food. Same thing happened with blood in anywhere of your body. Like if you get a bruise, it will eventually go away. Same with the brain, but because sometimes brain has like way more of blood, so we have to drain it out. But if you wait over time, your body tend to like digest it, kind of reabsorb it back to your body. That's why it's like the more longer you wait, the blood gets more and more look alike like the tissue in your brain. and then eventually it would just go away. So very bright color means it's very recent incidents that causes the thing. Yep, and then by how we determine what kind of hemorrhage it is the location. So this is, you can see like this part is the brain, and it is inside the brain, so it's intracerebral. And then this thing, this two little black color spot, it is the ventricle in your brain. So if the blood is inside the ventricle, like this case, so it is intraventricular hemorrhage. So I think the more commonly seen one are these two, the subdural and the epidural. Oh no, this, sorry. This is very not sensitive. Okay, so coming back to subdural and epidural. So dural is like a sheet protecting your brain. It's in between your brain and your skull. It keeps the fluid in your brain, like not leaking out. So subdural, this is your brain. Subdural happens underneath the dural and between your brain. So it shapes like this. So that's why when the blood comes in, it fills up this space, the fluid space. That's why it looks like crescent moon. Versus if it's epidural, it's above the dural, and then it's between the skull and the dural. So this is like a sheet of paper. It's very flimsy and stuff like that. So when the blood fills out, it kind of pushes it down. That's why it looks like biconcave shape. So that's how people differentiate between these two. I think this two is the most confusing one. Does that answer your question? Thank you. Okay. So like I said just now, CT scan is made out of Hounsfield unit. So air, we can see the Hounsfield unit is -1000, and then water is 0. CSF fluid is about 10 because we have mineral in our CSF fluid. And then white matter and gray matter makes up the brain. And this is the value for the brain. And then blood is right here. This is actually for acute blood. If it's for chronic blood, it's actually fall under this brain's range. And then calcium, you hear metal, you'll be like 1000, or like skull, because skull is very white, very dense. And then, okay, so right now let's talk about CT scan formatting. So we have generally the most commonly used are DICOM and NIFTY. So DICOM is like the raw CT file that you get. Once you get a CT scan, the clinician will send you a file that is DICOM file. It's unprocessed and it contains a lot of metadata in it. NIFTY file, and one thing to mention is DICOM file is if you get a CT scan, you'll get a folder with like 40 images in it. So each slice is an image in DICOM format. So if you have to load the entire folder in order to get the whole scan. Versus NIFTY format is just one file. So they combine all this different stack of scan of your CT and merge it into one file. So it is easier to manipulate versus to DICOM because now we're talking about one person having 40 images versus one file. So for DICOM, it's just easier for clinician use because you can see the metadata, you can have literally all the patient's information within the scan itself. And NIFTY, we take the metadata away, but we keep the images itself. So it's easier for research to use, easier for storage and stuff like that. And NRRD file, Sharada will talk more about it later. It is used in Slicer when you try to manipulate the CT scan. So underneath here is just the same table, but just discussing about like when to use it and what supports it. I wish we have a mouse. This thing is so not sensitive. Okay, so right now is the fun part, the hands-on part. So all you have to do is you click play. So every time when we start coding, just a show of hand, do you guys know how to code in Python? Have any experience? Okay, so that's pretty much the majority of the people. So you can just run oh no, I have to sign in. And I have to do my authentication. Okay, so let's try this again. Sorry about that. Okay, so we have to run the Python packages. It's gonna take like a couple, like 30 seconds for this first part to load. And the second cell is literally just import whatever you just installed just now. That's way better. Okay, thank you. It's very sensitive. Yeah, that's better than this one. Thank you. So after you load the file, I have included the raw data, the DICOM raw data over here in my Google Drive. So all you have to do is click the play button. And then the raw data will be downloaded. This is a DICOM file. So I want to guide you guys through today from downloading a DICOM file, having a whole stack of DICOM, and then convert it to Nifty and then manipulate the data from a Nifty format. And then after we downloaded the Python file, we just run this code. This code is just to show you that it has been downloaded. So you see in the DICOM file in the folder, we have all sort of .dcm file. So each of them is one slice of the CT scan of your head, of this person's head. And then we have to print the directory just to make sure we all have it. So it's printed, so it is there. Oh, no. Okay, just to double check. And then, so here first we want to display the image. So that's the code to write how to display an image. So you might see, hey, this image doesn't look like a brain at all. So because this whole thing is because of pixel and how you want to display the pixel value. So next step is step number 4 is to change the range of settings so that you can see what you want. So what do I do here is there's thing called window center and window width. You have to change it to the width where you can see the soft tissue. You can also change it to a different range where you can investigate the bone. Depending on what you're investigating, you just have to change the window and width setting. So over here, we change it to the soft tissue setting. So here you can see there's like this is hematoma over here. Now we successfully load a DICOM image and you can see it here.
How do you know that these numbers, 15 and 100 corresponds to?
Sorry, I cannot hear you.
Like, so if you go up, just go step 4.
Yep.
So you have this window center and window width.
Yeah.
And like 50 and 100.
Mm-hmm.
How do you like choose these numbers? How do you know that they correspond to
What?
you want? So if I do like 60, 80,
Yeah.
or is it valid or it's like some standard numbers?
Yeah, so it's actually it's applicable for every single scan. So all I have to do is I basically don't remember all this number on top of my head.
But it's like some standard. Like
Yes.
Okay.
Yes, it is very standard. If you just do a Google search, hey, I want to see the window width for the bone, so you can just one is the top, one is the
It's like a machine setting.
yes, it's like a very standard settings. You can just change it to whatever we can try one example, like 200 to 250. And then you will see a totally different display. Yep. So right now we have to right now we want to see the full display of the metadata of the DICOM file. Like I said just now, DICOM file has a lot of metadata in it. So you can see what type of body part is examined, and then where's the thing collected. Okay, but just so you know, this particular CT scan has already been de-identified. So everything you see here might not be true, but only the setting of like how the parameters of the CT scan is true. But anything related to where this CT scan was taken, about the patient, any location, anything like this has been de-identified. That's why some of these are not true. They have been modified. So here's a whole list of it. You can see it's very long. But sometimes we don't need that. It's literally noise. We only need what we want, right? So you can write another code, which I provided here. You can just go up here. Let's say I want to see the largest image pixel value. All I have to do is copy this line and then just post it right here, and then this code will do it for you. So over here, I wrote a short little code just to extract what I need from the DICOM metadata. These are the stuff that I use more commonly than the others. So this is just a snippet. Instead of like going through the entire list here just to find what I want, I can just write a smaller code, only extracting what I need. And then over here, you can see here, the step 7 is I am teaching you how to de-identify. So if you are doing research and you extract raw data with patient information in it, you have to de-identify before you transfer it out of your personal laptop and stuff like that. It's HIPAA compliance. So over here, you can see like originally, this is the example value, and then this is after. Over here, if you just load this code, it will show you what is the before and what is the after the identification metadata. So you can just manipulate this code to whatever you want as well to de-identify before taking it out. Okay, so now we go to, so that was the entire DICOM. So right now we're going to Nifty. I have to like glance through this pretty fast. My time's running out. So here's just, this code is just, let me run this one first, to teach you how to convert from a DICOM folder into a Nifty format. Because DICOM is huge, it's many, many images over there, very hard to manipulate. So for research purposes, we always convert DICOM format into Nifty before we use it. So this code is teaching you how to install from the GitHub of the DCM to Nifty converter. Once you have this converter, you can just run this code, and then it will convert your original DICOM folder into a Nifty format. So we have to finish running this. It's gonna take like, because it's installing, it's gonna take like a minute or two. But without running this, we cannot run the next code as well. But let me when it's running, I'm just gonna tell you. So DCM to Nifty, we're calling the application to help us convert a DICOM folder into a Nifty folder. And then here, I'm just gonna print to make sure, I always print stuff just to make sure your folder is there and everything it works as you want it to. And then step 3 is just loading up the Nifty file to investigate what's the difference. And then, okay, let's see, this is done. Okay, it says successfully installed. So we can move on to, okay, this is converting it. So you can see it's like everything conversion is done, print. So you can see case study 1, we have 3, after you convert to Nifty, it has 3 different file for you. One is the regular Nifty file, which is look exactly the same with the DICOM. Second, we have a JSON file. JSON file is pretty much how they store the metadata. And one time, if you ever want to convert a Nifty file back to a DICOM, you would need this JSON file to bring back the metadata. And then the tilt correction one, I'll show you what's the difference between the regular and the tilt correction one here. So here, I just want to make sure the Nifty shape looks correct and how the voxel dimension looks like. Step 4, visualizing it. So here you can see it is still look the same as before I switch the window width. Here, again, I adjust the window width. So you can see this is the exact same CT scan. So here, part 3 is understanding the 3 different output files. So right now we load the output files, the nifty format one, and then make sure the shape. Look at the original shape is 512, 512, 40. It is similar to the DICOM versus the tilt corrected shape is 512, 622, and 42. It is very different now. So let's see what are the difference. Oh, not to mention, DICOM uses a different coordinate system than Nifty. So every time you have to compare your DICOM file to the Nifty and see the Nifty format is actually flipped because it uses a different coordinate system. And I have posted it here. So you can read it if you are interested, but I'm running out of time. I'm so sorry. So here, after we apply the window, so this is the tilt corrected Nifty format. So here in this Excel plane, it doesn't look much different. What is tilt corrected? You cannot see it. So let's see at the sagittal version. So this is before the tilt correction, and this is after the tilt correction. Most of the time, patient go into a CT scan, they don't go in flat. They go in an angle just so the radiation doesn't hit the eyes and stuff. So the bed is a little bit tilted, and the tilt angle is actually written in the DICOM metadata. So the DICOM to Nifty converter actually used that metadata to tilt correct it. So let's say if you want to manipulate the data, you have to decide you want to use the regular one or you want to use the tilt corrected one. It all project dependent, just so you know. And this is the JSON file, which it has all the metadata that you need if you ever want to convert it back to a Nifty. And here's also extracting the same information as the DICOM that you will see. So in summary, the tilt corrected version, if you're planning to do some 3D modeling, segmentation, or alignment. And then part 4 is just some very basic thresholding. So thresholding is basically just, I want to isolate the Hounsfield unit that falls into the range that I talked about just now. If you want to isolate air, you use the -1000. If you want to isolate brain, you find the brain Hounsfield unit and then you isolate it. So the first one is I isolate the skull. So you see only the skull is displaying. And then second is the soft tissue. So I take away the skull and only the soft tissue is left. All you have to do is play around with the Hounsfield value, which one you want to display and which one you want to take out. And then here, there's something wrong with this. Oh, thank you. So this is the threshold for the acute blood. So we want to isolate just the acute blood, but you can see obviously the surrounding brain structure also look kind of similar. So you have to do additional segmentation in order to just isolate the blood itself. And then here, so here I take a while. So above here, you can see this is the outside. The outside is actually our scalp. So you can still see a lake, because I just took the skull away. I didn't take the scalp away. So over here, you write another code, only keep the largest island. That's how you do like basic segmentation. So here I want to quickly talk about how to identify CT artifact, because if you were to do something with CT scan, you would like see how to identify. It's very important. First, you can see this is motion. People are moving. That's why it's kind of like disorient brain. This is not the person is fractured, but because of motion. And then you have a bright metal. If sometimes it has a metal in your brain, then you take CT scan, it will affect the CT scan, the quality of the CT scan. You can see the metals right here. Sometimes it can be a drain placement after they went for a surgery. And then beam hardening, like because CT scan, it is beam shooting at you. So sometimes only the slow beam or high beam that's absorbed into your CT scan, but not the other. It is all about balance. So it looks like this. All you have to do is just get another CT scan redone, because the radiologists can't read it. And then how to minimize it. just ask patient to remain still. This is all for people who take CT scan. So machine learning based. So there is many publication about how if you encounter one of your scan like this, let's say you have like only 20 patients to work with, and like half of them have CT artifacts. So what do? You need the data. They are very precious and important. So you can also use machine learning based artifact reduction. So like what this paper do is, initially this is like a metal kind of artifact, and then all they do is put it into a CNN structure, something like that. So when the image get into the very low dimension, it reconstruct it, and then when it put back to the high dimension, it kind of fixes it. So I have included the publication here. If you're interested, you can read more. But yeah, thank you. Sorry if I have to rush through the last part. If you have any question, please ask me.